Hello and welcome to two FRQ questions that I want you guys to work through. At this point, you should have already tried yourself to work through these two. They were questions 3 and 6 because these are the two FRQ questions that are most relevant to what we've been learning so far. So we're going to go ahead and work through these and see sort of how they're supposed to be done. We'll look at maybe the scoring guidelines later. And anyway, let's go ahead and get started. So a company designs spinning toys using the family of functions. They give us the equation. C is some positive constant. Okay. Each spinning toy is in the shape of the solid generated when such a region is revolved around the x-axis. So that will be important later. So the idea is that essentially you're taking this curve and you're just sort of taking it around the x-axis and revolving it, sort of like this, right? And so it's creating a bunch of sort of rings, and the volume is based on these rings, right? So that's going to play more into one of the later parts down there. But we'll just start with part A. So part A says, find the area of the region in the first quadrant bounded by the x-axis in the graph and the equation. And they also give us a nice value for C. But essentially the idea is we want to find, this area here. Right? What is that area? Okay, and C is 6, right? So we have the equation. Right, so far we have y equals 6x square root of 4 minus x squared. Okay, we're integrating that from 0. We know where the starting point is. Do we know where the ending point is? Well, we can kind of easily see it, or you could solve for it, right? In fact, let me go ahead and do that. How would we solve for that point? We would do it by setting y equal to 0. And sort of looking at what makes this true. So when does that equal 0? Well, it's either when x equals 0, right? We already know that solution, but it's also when x is equal to positive 2, right? We're in the first quadrant, so we're only considering positive solutions here. So this number is at 2, right? Or that point, sorry. This is at 0. So when we integrate this curve, we're integrating from 0 to 2. In fact, I shouldn't put the integral there, right? Let me go ahead and set it up over here. We're integrating from 0 to 2, just that right side of the equation there. Of course, you always need to have a dx there. So with any luck, this red integral will give us the area that we're looking for. And you might notice something. You can't just immediately start calculating this integral. You might notice from the section prior that this is a u sub case, right? We have a 6x here and an x squared there. Usually when you have powers of x, where one is exactly one higher than another from another portion of the integral, that's a sign that you need to use u sub. And so what I'm going to do, you can substitute out for the x squared or for the 4 minus x squared portion. I'm going to go ahead and do that. I'm going to say that this is u, right? So we'll set it up over here. We'll say that u equals 4 minus x squared. We're going to take a derivative of both sides here. So that's equal to negative 2x. And because this is the way I like to do it, right, I want to turn that negative 2x into a positive 6x. So I'm going to multiply both sides by negative 3 and by dx to get negative 3 du equals 6x dx, right? There's all sorts of ways you can do u sub. Just make sure the way you're doing it gives you the right answer. This is just the way I do it. So yeah, this negative 3 du is going to go here. We have the u going here. And these numbers are going to change too, right? So if I plug in 0 into the u equation, it tells me that u should be equal to 4. So this guy's going to turn into a 4. And this 2, when I plug it in, turns into a 0. All right, so notice how our boundaries are going in the opposite direction. They're going from a higher number to a lower number. All right, that's okay. Let's see, we're going to have square root of u, and then we're going to have times -3 du. Now, you could calculate the integral this way, and it will still give you the right answer, but what I might do is I might actually change the bounds. I want to go from lower numbers to higher numbers, just because that makes a little bit more sense to me. But if you do that, you're going to have to get rid of that negative, right? It's going to turn into a +3. So our integral is going to change to +3 times the square root of u du. I just moved it to the front just because that's usually where constants go. So now let's calculate the integral. So the antiderivative here is going to be u to the 3/2. 3 divided by 3/2 turns into 2/1, so just 2. In fact, it's kind of written a little weird. Let me move this down here. We're just going to end up with a coefficient of 2. You can check that by taking the derivative and going the opposite way. You should get your integrand. And we're going from 0 to 4. All right, so let's see what we got here. 2 times 4 to the 3/2 minus 2 times 0 to the 3/2. Okay, so this term goes to 0. That's nice. 4 to the 3/2, right, take the square root of 4 first, that's a 2, and then now cube it. So that's an 8, right? So 2 times 8 gives you 16. So yes, they will expect you to know probably how to do fractional powers like 3/2. I mean, it's possible you might have 5/2 or something like that, or maybe 2/3. So like, make sure you know what does a fractional power tell you, right? Remember, x to the 2/3 power is the same thing as the cube root of x squared, right? In this case, we're talking about, just to make it more clear, we're talking about 2 times the square root of 4 cubed. And, you guys know I like this one, right? Because 4 cubed is 64. Square root of 64 is 8. Right? 64 is a square and a cube. But the point is, yeah, your answer is 16. And the area, remember, it tells us that x and y are in inches down here. And we're doing an area, so this must be inches squared. They're probably going to expect those units there. All right, so that's part A. And I might go ahead and label that over here, part A. Part B, it is known that for y equals whatever, that the derivative is this. So they just give you the derivative. That's really nice. For a particular spinning toy, the radius of the largest cross-sectional circular slice is 1.2 inches. So this phrase here, that's basically referring to if you just took a big knife and you sort of chopped the spinning top at the point where the radius is the largest, right, which would be kind of around there, maybe a little bit behind that point, around there. So if we chopped this and we looked at, what is sort of the radius of this circle here, they're claiming that the radius here is 1.2 inches, right? That's the largest cross-sectional slice because that's the highest output of the function. So they're saying it's 1.2. The question is, what is the value of C for this spinning toy? Okay. So how do we find this out? Well, you might notice just by looking at the picture, like intuitively, you can tell that the largest cross-sectional slice happens when the first derivative is equal to 0, right? So you have a horizontal tangent line there. It's a maximum of the function, right? This is when dy over dx is equal to 0. Okay, well, if I know that information, let me go ahead and just turn this into a 0, and maybe I can solve for C. Well, let's see. I'll go ahead and do the work maybe down here, right? So B. So let me solve the equation. 0 equals C times 4 minus 2x squared. Okay, yeah, just that. And then the square root of 4 minus x squared. Okay, so when this equals to 0, that's when we have the largest cross section. So this is equal to 0 when the numerator is equal to 0. So I can sort of simplify this a little bit. I can just say we're looking for when c times 4 minus 2x squared is equal to 0. Now this equation is only equal to 0 either, you got two cases, when c equals 0, but if you think about it, that doesn't make any sense, right? That would basically get rid of your whole graph. If you made c equal to 0, there wouldn't even be a spinning top at that point. So this is not what we're looking for sure. That solution doesn't make sense. But the other way, or the other case, when this equals to 0 is when x is equal to, if you think about it, right, the square root of 2. Now, that's not c, obviously, but that does tell us something important. That does tell us that this location right here is exactly the square root of 2. So maybe we can somehow use that information along with the fact that this height here, or basically the y value of this point, is 1.2 inches. Well, what can we use? We can use the original equation, right? So if we sort of piece this together, what we can say is that c times x times square root of 4 minus x squared, right? We want this to be equal to 1.2, and we know when we've hit the largest cross section. We said that was at square root of 2. So really, all of these x's in this equation become square root of 2. Square root of 2. And this is square root of 2 squared, right? We're plugging in for x there. Okay, so now, right, let's solve for c. Let's solve for c. So what do we get? We get c times the square root of 2. This becomes the square root of 4 minus 2. That's equal to 1.2. Okay, so this is c times the square root of 2 times, this turns into the square root of 2. Oh, that's awesome. All right, square root of 2 times square root of 2 is 2, right? So we have c times 2 equals 1.2, and when we solve that, that tells us that c is equal to 0.6. Nice, right? Divide by 2 on both sides. So hopefully you can kind of see what I was doing, right? Because we know over here at x equals square root of 2, the y value is equal to 1.2, right? So I was basically plugging in both those pieces of information because we know exactly where this point is, and using that to solve for c. C was the only unknown variable at that point. So that's part B, right? So 0.6. Now, does it have any units? Possibly. Maybe. I'm not quite sure. I don't know if they'd necessarily want the units, but I guess we'll see in the scoring guidelines. All right, part C. Part C. For another spinning toy, the volume is 2 pi cubic inches. What is the value of C for this spinning toy? So now here's where we're going to have to really think. We're going to have to actually visualize what this volume is, right? Because it's a volume of revolution So we want to imagine a bunch of rings being created. And obviously on the AP test, the best you can do is sort of like draw pictures. So you want to do a bunch of that to sort of get a sense for, okay, what does this thing look like? In this case, what I'm going to do is I'm going to show you guys a nice helpful visual aid here. So if I jump over here, I've written this program that essentially follows this exact same curve for this problem and creates that volume of revolution. So if I zoom in, you see that red, it's covered with all those green balls, but that red curve is the curve we're dealing with, and I chose to make C equal to 1, so it's a little steeper. I just chose 1 for simplicity. But if I press play here, we're going to see these balls trace out the exact curve at those points. So they're all at the same x-coordinate, and they're creating these little radiuses. And so if we're talking about a volume, these are essentially, these circles are going to be filled in and sort of turn into cylinders. So watch this. I'll play it. And this is basically a nice way to visualize what these tops actually look like. I mean, they really do look like spinning tops. So the point is, if we're going to calculate this volume, this is how we need to think of this integral. It's a bunch of very skinny cylinders where the radius of each cylinder is defined by the output of the function at that x value. And then we're going to integrate along whatever integral for the entire spinning top. Right? And we know that the end of the interval, no matter what c is always going to be 2. If you plug in 2, the function spits out 0. Right? So that's for sure. And for different c values, obviously, you're going to get like really wide tops or very skinny tops. It's going to change sort of how big or how fat like this spinning top is. So let's go back to the problem here. So the volume is 2 pi. And this is going to be equal to some kind of integral. We're obviously integrating from 0 to 2 because, well, we know that here's 0, here's 2. That's not going to change no matter what c is. And we want to integrate basically a bunch of circles, right? We're thinking not about Riemann sums, but about little cylinders, right? So think about, how do you calculate the volume of a cylinder? Well, you need a height to the cylinder. Now notice these cylinders are sideways. So really the height in this case, if you think about it, is dx. That little dx, I mean, ideally we want to shrink that height to 0 so that we get more accurate of an approximation. So that's what our dx represents, the height of each cylinder. And you have the height times the area of the circular face, right? So what is that circular face? It's going to be pi times r squared. Now what is r in this case? Because r is changing. It's changing according to this function right here, right? So you plug in a certain x value, it spits out the radius for that cylinder, right? So we're actually squaring this entire function. So this is where we put cx square root of 4 minus x squared. And this integral right here calculates the volume. I know it looks kind of complicated, right? But this is the integral we need to set up. So now let's go ahead and sort of try to solve it as far as we can go. So first of all, let's simplify this integrand. Let's simplify the integrand a little bit before we even do the integral. So 0 to 2. If I square everything, I get pi times c squared times x squared. And then we get 4 minus x squared, right? The squared sort of cancels out with the square root there. So we just have that term, and dx. One thing I might do too, so I'm going to go ahead and take these are constants, right? Pi and c. I'm just going to move them to the front. and I'm going to distribute in the x squared, right? In fact, I'm gonna put this down here. So I'll have 2 pi is equal to pi times c squared times the integral from 0 to 2. And when I distribute the x squared, I get 4x squared minus x to the 4th dx. And I move the constants to the front because I notice if I divide both sides by pi, they cancel. Right, so that's good. The c squared is just going to stay there. We'll deal with that later. But now we kind of have everything we need to do the integral, right? So let's focus on this integral here. So we have c squared, and we got to find the antiderivative. So we're going from 0 to 2. So we're going to end up with 4x cubed over 3 minus x to the 5th over 5. All right, so for problems like this, you definitely need to be kind of quick at getting those, right? But yeah, those look like the correct antiderivatives of those two. Let's go ahead and calculate this. So we have c squared, all right? And then we have, let's plug in 2. So we get 4 times 2 cubed over 3 minus 2 to the 5th over 5. And then minus 4 times 0 cubed over 3 minus 0 to the 5th over 5. And what's nice is this whole term is 0. So that makes our life a lot easier. Let's keep going here. So we have c squared times, we get 8 times 4 is 32. So 32 over 3 minus, looks like 32 over 5. Okay. Let's get a common denominator. Remember that you don't have a calculator here. You have to do all this by hand. So we have c squared times, let's see, common denominator of 15. So I know that's going to be true. 32 times 5 is 150 plus 10 is 160 minus 32 times 3 is 96. All right. Oh man, we're running out of room here. It looks like that's going to be c squared times, let's see, minus 96 minus 100 plus 4, 64. 64 over 15. Okay, cool. So let's take it all the way back to where the 2 pi is, right? Or sorry, we got rid of the pi. We only have a 2 over there. So just to summarize, right, 2 is equal to c squared times 64 over 15. And at this point, right, just divide by 64 over 15. Right, you get 30 over 64 equals c squared. Simplify, you get 15 over 32 is equal to c squared. And then, of course, take the square root. And remember, they told us c is positive. So it's the positive square root of 15 over 32. And that is your final answer. Wow. That took a really good amount of work there. And you had to set up an integral very conceptually, right? So anyway, that's part C. That is the correct answer. I've already looked at the scoring guidelines here. So we'll look at those in a bit. Now let's jump over to problem 6. So we're going to skip this one. You guys could probably do this one based on what you know. But we're going to skip it. You guys could definitely do this one. Absolutely. This one's number 5. If you want a straightforward FRQ problem, definitely try number 5. But yeah, let's do number 6. So slope fields. Yes. So let's read the problem and we'll get started. A medication is administered to a patient. The amount in milligrams of the medication in the patient at time t hours is modeled by a function y equals a of t that satisfies the differential equation dy over dt equals 12 minus y over 3. So differential equation. At time t equals 0 hours, there are 0 milligrams of the medication in the patient. Okay, so that's, right off the bat, that's telling us that our solution is going to go through 0, 0. That's what that is interpreted as, right? They tell us what t is, and 0 milligrams represents the y. So we already know a point here. Part A, a portion of the slope field for the differential equation is given below. Sketch the solution curve through the point 0, 0. So yeah, that's what we basically inferred already. So we want a solution that goes through this point, right? And we know all the slopes. And so we want to sketch a solution that makes sense here, right? And if you want a very straightforward approach where you don't have to second guess your answer, just imagine, take the simulation sort of approach. Imagine there's a ball here at 0, 0, and just have it follow the tangent line for just a little bit, and then pause, and then figure out what the new tangent line would be at this spot. And it's basically the same. And then have the ball follow the tangent lines there. Maybe that was not steep enough. Let me do something like this. I don't know if you guys can hear it, but there's an ice cream truck nearby. I'm not going to buy that. It's too expensive. Anyway, and just keep doing that approach, right? So let's say the ball's here, follow the slope of the tangent line. Right, now the ball's here, follow the slope of the tangent line, right? That's just basically a foolproof way to make sure you're doing this right. And overall, what you should get is something, kind of like this. You just want to make sure the slopes of the tangent lines are basically lining up with the slopes nearby. So we get something like this. And what you should definitely have in your solution is essentially you have an asymptote here, right? The slope gets closer and closer to 0. And so this is like a little asymptote here at whatever this value is that the function approaches, right? And there's no possible way your solution is ever going to go up here. If you have part of your solution up there, they're probably not going to give you the points there. But your function should basically be, it looks like it's kind of concave downish, and then it should approach that sort of horizontal slope eventually. And that sort of makes sense, right? If we're talking about medication in a patient and it's being administered, eventually it's going to reach some sort of equilibrium value, and then it's going to hover there the moment you put it into their system. So that seems fairly realistic. All right, part B. Using correct units, interpret the statement, the limit as t goes to infinity of a of t is equal to 12 in the context of the problem. All right, so they told us what the output of a of t is, right? Right, if we know that the y's, or the sort of the outputs of this function, are the milligrams, right? When they're saying that the limit is equal to 12, they're saying that the milligrams are sort of approaching the value of 12. Or we're approaching 12 milligrams as time moves forward, because t always represents time. I can't think of a single case where t represents something else. So let me make sure I know what the units for time are here. It says in hours, right? And let me reread their explanation. So medications administered to a patient, the amount in milligrams of the medication in the patient is modeled by the function. Okay. So maybe something we might say here as an interpretation is that maybe we might say as hours move forward the amount of medication in the patient approaches 12 milligrams, right? And yes, you need to include all those little details. I know it's a lot to write down, but they're going to be, when they say in the context of the problem, they want you to actually make this like a real world situation. So, you don't have to use the exact same words. You might say as time goes on, or as time approaches infinity. You could even say that too, right? But they want to hear about the medication. They want to hear about the patient. They definitely want you to use these units. Right? They want it to have flesh and blood on your number. It can't just be a number. You can't just say, A of t approaches 12. That's not going to get you any points. Right? That's what the context is a real world situation. You have to include the details, right? So don't forget that on the test. I don't want you guys missing easy points just because you were getting lazy here. Okay. Part C, use separation of variables on this function to find y equals a of t. So that's why they didn't give us the equation. We're going to solve for it. Okay. The particular solution to the differential equation with initial conditions 0, 0. Okay. Yeah, we knew that, right? We already knew. We're basically solving for the equation for the curve that we drew in part A. So that's kind of cool. So how do we solve this thing? Well, we probably want to go ahead and maybe multiply by 3. Yeah, we could do that. So we end up with 3 dy over dt equals 12 minus y. Now you might be tempted to add y to both sides, but that's not going to be a solvable differential equation. I know it seems like it would be, but it wouldn't be, because in the integral, right, when we integrate, that dy has to be multiplied somehow or divided by an expression with y. You can't have the integral of dy plus y. That doesn't work, right? You also can't have the integral of y plus dy, right, for the same kind of reason, because that's not giving you the area of a rectangle, right? So yeah, don't add y to both sides. But what you could do, which we're about to do in a second, is divide. In fact, I probably should have left the 3 over there, but you could divide both sides by 12 minus y. You could do this, right? And this will turn into 1. And so we have 3 over 12 minus y, dy dt is equal to 1. And of course, you want to separate those variables. So I know this is kind of redundant. Let me go ahead and move the 3 back over there. Let's divide by 3 on both sides. Let's divide by 3 on both sides so that we get this. So, and 1/3 over here. And then let's multiply by dt on both sides. So we end up with dy, I'll put this in the numerator here, to 12 minus y, is equal to dt over 3. Now we've separated the variables. Notice how the y's are with the y's, and we don't have any t's, but that's okay. Usually as a general rule, you want to leave your coefficients with the independent variable, right? T is our independent variable. So anyway, let's go ahead and integrate. And sort of the question is, if you're getting stumped by the left side, what is that antiderivative? It's not going to be y to the -2 or something like that. This is that special natural log case. Oh, okay. Yeah. This is that special natural log case. All right, so this is going to turn into the natural log of 12 minus y, right, on the left side, with a negative sign in front, right, because you got the chain rule happening. And if you don't believe me, right, take a derivative. Take a derivative, and you will see. This turns into negative 1 over 12 minus y, and then because of the chain rule, we have times negative 1. And the negative cancel, and we're left with the integrand. So it works. It works. That is the antiderivative. You can always check that. Don't be afraid to check your antiderivative. So we should have a negative in front. On the right side, remember, this is just the constant 1/3. So the antiderivative is going to be 1/3 t, and then plus some constant, right? Now, what some people do is instead of solving for y at this point, it might honestly just be a little bit easier to just go ahead and plug in our initial condition first. Down here, just so we can find out what c is supposed to be, and then we can go ahead and solve for y to get like the final equation for that. So yeah, let me go ahead and do that. Let me plug in 0 for y, and then 0 for t. Well, that's going to get rid of that term. So we have c equals this thing. Okay, that means that the natural log of 12 is equal to negative c. And then, well, actually, you know what? I shouldn't have done that. Yeah, no, we have c. We have c, right? It's actually easier than what I was thinking. So c is just the negative natural log of 12. Right, so that's a good example of, well, this isn't our answer, right? But that's a good example of why sometimes you might not want to solve for y until you've found your constant of integration. So now, let's go ahead and take our general solution, which is this guy. It's the general solution. And let's plug in our c. So we get negative natural log of 12 minus y is equal to 1/3 t. And then we said c was minus the natural log of 12. Minus the natural log of 12. Cool. Now let's solve for y. All right, so let's see. Well, let's multiply both sides by negative 1 to start. Right, so we have natural log of 12 minus y is equal to, remember that negative will distribute to both terms, so you get negative 1/3 t plus the natural log of 12. And remember, right, the move to get rid of natural log is you sort of base e both sides. And this thing will be the whole power on this e on the right side. Right, so these two will cancel. And we have 12 minus y equals e to the negative 1/3 t plus the natural log of 12. Now, and they're going to expect you to actually do this, but you can simplify this a little bit further, because if we look at the scoring guidelines, they show even more steps after this. They want you to sort of split up this power here and deal with this natural log of 12. They don't want you to leave it like that. So how can we split it up? Well, just use your exponential rules. Right? We have this times e to the natural log of 12. That's a valid rule, right? It turns addition into multiplication, right? So they're going to expect you to do that. If you didn't see that, right, you should brush up on your exponential rules. And what's nice about doing that is that this is now going to turn into 12, right? E and ln are inverse functions. So what we have here is 12 minus y is equal to 12 times e to the negative 1/3 t. And if we rearrange this a little bit, right, add y to both sides, subtract the whole right side there, you get that y is equal to, I'm writing kind of backwards here, 12 minus 12 e to the negative 1/3 t. And that is our particular solution. Right? That's the particular solution that goes exactly through 0, 0. And one good way you can kind of intuitively check that this is right is imagine sending t to infinity and imagine what the outputs approach, right? Do they approach 12 like the other part said? In fact, they do, right? The longer time goes on, the closer this term goes to 0, and you're left with y values that get closer and closer to 12, right? In the limit, right? So that is the particular solution. That's kind of cool. It's sort of like an exponential decay that's been flipped over vertically, and it's been translated up by 12. Kind of nice. Let's see, is there another part here? Part D. This will be the final part. A different procedure is used to administer the medication to a second patient. The amount in milligrams of the medication in the second patient at time t hours is modeled by the function y equals b of t. So I guess this is patient B. And it satisfies this differential equation. At time t equals 1 hour, there are 2.5 milligrams of the medication in the second patient. Here's the question. Is the rate of change of the amount of medication in the second patient increasing or decreasing at time t equals 1? And they want us to give a reason. Okay, so this is a problem that's a lot more conceptual. We're not going to be solving for some equation here. We're not really even giving a number. We're just sort of explaining what's going on. And notice what they're saying here. Is the rate of change, forget about all this other nonsense, right? Get rid of all these words here. We're math people. We don't care about details. Is the rate of change increasing or decreasing? Not is the function or the amount of medication, but is the rate of change of the amount of medication increasing or decreasing? This right here is talking about a second derivative. And if you didn't catch that, right, go back and read that and think about it. Is the rate of change increasing or decreasing? That's a second derivative. And namely, right, you know that the second derivative is increasing when you have concave up behavior. Or you know that the second... You know that the rate of change is decreasing when you have concave down behavior. Right, this is a rate of change of a rate of change. So what we're going to test here is what is the second derivative doing at t equals 1. And that's going to tell us if the rate of change is increasing or decreasing. Again, read that again. If you're still confused, right, think about it. Think about what they're really asking you. So the point is we want to find the second derivative. That's the first starting point. And they're going to give you a point just for doing that, right? Just for even trying to find the second derivative. So that means we got to take this function, take a derivative. And let me go ahead and use use the second derivative notation like that, right? So we're taking another derivative. The right side is going to turn into the derivative of this thing, which notice, right, we have an implicit differentiation. We have y and t in the same thing. And we're going to have to use the quotient rule. Oh, yay. Super fun, right? But we can do it. Right? So it's the derivative of the first times the second minus the first times the derivative of the second, all divided by the second squared, right? So I'm just going to set up all the parentheses so I don't have to worry about doing that later. Now let's do it piece by piece. The derivative of the top function, or the first function, that's going to be dy over dt, actually. So we have the first derivative in the formula for the second derivative. And yes, there's not an easier way to do this. That's actually what it is. Times the second, right? So t plus 2 minus the first times the derivative of the second. So that's going to be 1. All divided by the second squared, the bottom function squared. You just got to be really careful with the quotient rule. It's tedious, but as long as you're careful, you're going to do it right. So now, we want to figure out what is the second derivative at 1. Okay, well, if we plug in 1 here, what do we get? We get dy dt. I don't know what that is. If I plug in 1 here, I get 3. Do I know what y is at 1? Do I know what y is? I'm not totally sure. Oh, you know what? Actually, I do know what y is. Notice, right? At time t equals 1 hour, they tell us what y is. This is y, 2.5 milligrams. So yes, 2.5 milligrams. On the bottom, I get 3 squared. So my second derivative is, well, it's this is the closest we can get for now. If I could find what that first derivative is, I can figure out what this should be equal to, right? And then that answer should tell me if the rate of change is increasing or decreasing. So what is the first derivative? What is dy over dt at t equals 1, right? What is that equal to? Well, I have the equation, right? That's going to be 3 minus, again, we know what y is. It's 2.5 over 1 plus 2. Okay, that's going to be 3 minus 2.5 over 3. Okay. And honestly, it might just be best to leave it like that. Because notice when we plug it in, like we're not going to get a nice decimal from this. But notice how if we plug this in here, that 3 is going to distribute in. And it's going to get rid of that denominator of 3. So that actually, let's go ahead and leave that alone. And go ahead and just plug it in. So this is different work, right? So this is equal to 3 minus 2.5 over 3 times 3 minus 2.5 over 9. So just to avoid confusion, let me get rid of this part over here. All right, so that 3 is going to distribute in. We end up with 9 minus 2.5 minus another 2.5 over 9. Okay, that's 9 minus 5. Okay, that gives me 4. And then the denominator is 9. So that's positive. Our second derivative is positive there. It's positive, okay. Let me make sure I did my math all correct here. Okay. So what this seems to be telling me is that the rate of change is increasing at t equals 1 hour. This would tell me that the rate of change is increasing at t equals 1 hour because, right, they ask for a reason. If you don't give a reason, you're not going to get the point. Right? So what's the reason? Because the second derivative is positive, bigger than 0, at t equals 1. Right? That's enough justification to say what's going on. Right? So you just want to show them that you did the correct test to see if the rate of change was increasing or decreasing. So if you tell them that I checked the second derivative, then that's pretty obvious you did the right thing there. So anyway, that's part D. Let's go ahead and jump over to the scoring guidelines and see sort of what these say. So did we do all this right? Let me jump way over to question 3. Is that question 3? Yeah. So this was question 3, the spinning top. So it looks like you get 1 point for just setting up the correct integrand, just for setting that up, right? If you need to write it on your paper in order to get points for it, though, right? I know a lot of you guys try to do it in your head, but you're not going to get points for that, even if it's right. You got to write the actual integrand. You get a point for just finding the right antiderivative. So if you did both of those, that's already 2 out of 3 points. And then you get 1 point for the answer, too. And they'll probably expect you to have those units there. So anyway, it says the third point is earned only for the answer 16 or equivalent in case where a response only presents an indefinite integral. The use of the correct limits. Okay, interesting. Yeah, so it doesn't necessarily say anything about the units, but I would play it safe and always put those units there. So anyway, that was 3 points for part A. Part B, let's see. So you get 1 point for setting the first derivative equal to 0. That's nice. Easy points there. And then you get 1 point for the answer, which we found was 0.6. Says the second point can be earned without the first point, but is earned only for the answer C equals 0.6 with supporting work. So again, if you just write down 0.6, you don't show any work, you're not getting that second point. So, show your work on everything, like always. On part C, we get 1 point for the form of the integrand. So if you set up that little cylinder integration thing that we talked about correctly, that's 1 point. Limits and constant. Limits and constant. I'm guessing that has to do with, I guess, if you squared it correctly. It doesn't show very much else after that. That's interesting. I'm guessing they give you that point for just sort of simplifying the integral a little bit. Not sure what they mean by limits and constant there. You get a point for the antiderivative, of course. And then you get 1 point for the answer, of course. We got that answer as well. So that was question 3, and let's go down to question 6. Question 6. Nope, that's not it. Part 6. Again, calculator not allowed. So you see that you get 1 point for the solution curve. That should be, basically easy points, right? Notice how it approaches that asymptote there, right? Don't cross that horizontal line. But basically, if you draw something kind of like that, right, it says generally increasing and concave down, approaching the asymptote from below. The point is not earned if 2 or more solution curves are presented. Okay, so just make sure you draw one. Don't try to draw multiple ones and say a family of curves is your answer or something like that. Let's see, part B. Looks like we get 1 point in the interpretation. It says their interpretation, or this is an example, over time the amount of medication in the patient approaches 12 milligrams. Yeah, so notice, right, they point out the medication, the patient, milligrams, like they're using detailed words here. And notice the scoring notes, right? To earn the point, the interpretation must include medication in the patient or approaches 12 and units or their equivalents. So you need to have all those pieces there to get that point. All right, and then part C, use separation of variables. So you get 1 point for separating them, 1 point for the antiderivative, 1 point for finding the correct constant, and then 1 point for solving for y there. Okay, nice. Let's see, any other interesting notes down here? Okay. Part D. Oh, you know what? Looks like I made a slight mistake here. Oh, that's interesting. Okay, I'll have to check my work here, but you get 1 point for even using the quotient rule. That's nice. You get 1 point for noticing the second derivative was less than 0. So what mistake did I make here? What mistake did I make? I think I see it. There was a minus sign at the very front that I forgot, that threw off my final answer. But notice how I did get the right number. It was supposed to be negative. So I guess I probably would not have gotten that point there. But look at the interpretation, right? The rate of change of the amount of medication is decreasing at t equals 1 because the second derivative is negative. So that was the correct answer there. And the second derivative is continuous in an interval containing 1. I wonder if that second portion is truly required here. Let's see. Last, an attempt at using the quotient rule to find second derivative. Let's see. We're talking about the third point here. Okay. In this case, the third point will be earned for a consistent conclusion based on the declared value or sign of the second derivative. Okay, I think what is truly necessary is the sign of the second derivative, which I think we had the wrong sign, right? But we did use it as a justification. So I think we would have gotten the point if I had gotten that answer correct, but that's okay. Very, very tiny mistake. We did get the right number there, just off by a minus sign. So anyway, I've gone way too long, but hopefully it's been a good learning process. So hopefully you guys have sort of seen more about how the kinds of questions they asked, and notice I think someone had asked earlier the past week, would they combine U substitution with something else? And I think I had said no. I think it might have been Liam. But it turns out they did. They did. In question 3, they had a volume of revolution problem, and they threw in a U sub in there. So I guess I spoke too rashly there. So that kind of stuff is on the table. They like to be very, very tricky. So anyway, hopefully this was helpful. Gives you a better idea of kinds of questions they ask, and feel free to try the others, right? It's just all good practice. So maybe try that question 5 first. That's a really straightforward one. You're just finding, I think, an equation of a tangent line and a couple other things, but it's all abstracted. It's not like a word problem. And then maybe look at the others. There's a really good one about bacteria growing in a dish. And so you have to think about, it's another one where you have to set up the integral conceptually. You have to think about the actual sums and what they're supposed to represent. So that's a pretty cool one too. But anyway, take care, guys, and I'll see y'all back next week.